Cool. So how was lesson 7 so far?
Definitely not going to be the last time I have to look into RNNs.
Well, it may be the last time you have to look into RNNs because it's starting to look like we're going back to CNNs for a lot of this stuff.
Yeah, at least in the course, yeah.
Yeah, so were you saying something, Mahesh?
No, I think in a way it is good because the simpler structures you have, the better it is in terms of modularity.
Mm-hmm.
So if you can use the same kind of structures for different applications, it makes things much more simple. Is my viewpoint.
Yeah, I think Sebastian's going to be talking about some of this stuff, but I was reading through a bunch of these various kind of fall of RNN articles. There's some interesting stuff out there for sure. Sebastian, are you ready to go?
Yeah, I guess. I'm just gonna share my screen here.
Let me pause mine and you should be able to take over.
Can I take over yet?
Go right ahead. Yeah, there's a share screen button should be at the bottom of the window.
Invite participant share screen. There we go. Select the window application you want. Oh, you have to share individual windows. Okay.
You can do either.
Share session, I guess. Oh, share desktop. Tell me when you see it.
Got it.
Okay. So here's a timeline. Oh, well, I guess what I'm going to talk today about is mostly machine translation, like French to English, and or any pair of languages with machine translation. And I was going to talk about how convolution neural networks are used there, but I'll say something about that briefly. It's just kind of a big topic. Anyway, so here's a brief history timeline. So this whole thing, I guess they tried it with neural networks in 1987. The gentleman named Bob Allen, I think, here, and it was just it was a 50 vocabulary. 50 word vocabulary is, small scale stuff because that's all the compute power they had then. And, but that back then they had the idea of an encoder and a decoder. That's the picture at the bottom here. So the encoder takes in your source language and the decoder spits out the target language sentence. So these were just like binary. They didn't have embedding, so they're just binary inputs and something like I think 50 input lines, 150 hidden neurons, and so forth. So, but at least back then they had it was the idea of an encoder decoder structure. And then a few years later, this is actually 1992. I think a gentleman named Chrisman improved on that somewhat. I don't know. His scheme was called RAM. I think recursive auto encoder memory. That's what it stands for. I don't know what it is, but I think it had some sort of recursiveness to it. And then it was quiet for about 20 years when the second wave of neural networks died, and then around 2013 it started picking up again. And what's interesting about this is we're used to thinking of recurrent neural networks as the sort of the poster child for machine translation, but when it during the third wave, when it picked up, the Kalkbrenner used a convolution neural network. So you know, it started as convolution in the third wave, and then a year later, I guess there's two groups, one from Cho and the other one from Sutskever, and I guess so. Kalkbrenner used he used CNN. Hang on, sorry. He used CNNs, and Cho Sutskever used an LSTM, and Cho used what is it? A GRU, which I think we learned in this lesson. But so that's, you know, that's when the really good interest results came, and yeah, and so besides this, the use of these GRU and LSTM units, I think the more recent stuff that they've added in the past couple of years is something called attention. And attention would just fit right into here. You just some sort of mysterious attention block, whatever that is. So that's a sort of like a brief history. And, you know, let me go into this decoder encoder thing a little bit. These can be LSTM, or they can be CNN, or they can be GRU, and likewise with the decoder. So what this let me I just want to show a video of what's not really considered encoder decoder, but I mean what these things do is they just take an input, they have some hidden neuron activations that represent what they are, and then that's an encoder, and a decoder takes that and puts out this target language. But Jeffrey Hinton has an interesting representation of here's Hinton's, like about 10 years ago. He made just made an MNIST classifier. The bottom here, I don't see. Oh, I don't know if you can see my mouse, but the bottom here where the handwritten number 4, that's your input. And then it goes into 3 hidden layers, which is the staticky looking thing. Here's a 500 neuron hidden layer, another 500 neuron hidden layer, of 2000 neuron hidden layer. And then the output is a classification of 0 or 5. White is what it classifies it as. But so you can look at this as an encoder decoder all in one, right? It just takes in an input and it runs it, and you know, the higher up you go, it's an encoding of what that is. And then if you run it backwards, it's a decoder. It's a generative thing. Let me just play. I don't know if you can see this brief clip of it, but no. I don't know. Can you hear it?
We see it, but I don't think we're getting the audio. Getting a little bit of it.
Okay. Well, maybe this is not such a good idea then. But basically, you know, an encoder or decoder just works in opposite directions. That's what it is.
I think the idea behind this, to have an encoder decoder system for language translation at least, is that you can so let's say you have 40 languages you want to translate to, and if you would build a neural network for each of the language combinations you can have in this room, then that would be a lot of neural networks you have to train. And the idea behind this is that you can, for each language, train one encoder and decoder, and then you can just swap them out
Yeah, I think, yeah, you're absolutely right. And yeah, so you don't have to, if you're doing 80 languages, if you want to translate, there's, 640, 80 times 80 is 6,400 combinations. You don't want to train 6,400 combinations of languages. You just want to train 80, right? So yeah, you're right. And these encoder decoder neurons, they're basically, I guess what we call them, they're language models, which we've seen in class. So that's basically what they are. That's how you train them, as a language model. And,
I mean, that's very interesting. You kind of create this internal state of the language that a human can't even read, but it's kind of interchangeable between different languages. That's pretty cool.
Yeah, and what this internal state, I guess Hinton calls it a thought vector. You have in our word embeddings, you have word vectors. If you string a bunch of word vectors together and encode it, and then, so he calls it a thought vector. So a sentence is really a thought. You encode everything into a thought, and then you decode that thought into your target language.
Yeah.
So, what else can we say here? I guess in the early neural networks here, we don't have any word embeddings, but then later on in this scheme, this is when we do the word embeddings here. So that's the other thing that was added to in the third wave.
And how does a convolution for language or for text look like?
Okay.
Do you know that?
Yeah, a little bit. So the convolution would work at this encoder region, and let me show you something that I was looking at. I think here is. See if we can make this bigger. So here is a network architecture for that. This would be the top part of the picture here. You have the word, the sentence, they agree. You put it through word embeddings, and then you take you put it through a convolution. So the convolution is through time. And it's really a one-dimensional kernel, or one-dimensional filters, as we call it.
Okay. Okay.
And I'll come back to that in a little bit. And then you put it, I guess through some nonlinear weighted sum kind of thing after that. And then you have another convolution down below there, and it goes through some attention schemes and stuff like that. But the convolution part, I guess I'll focus on is let's see here. That part confused me a little bit, so I will play with it. So you have your target sentence. What was it? They agree. They agree on meeting. They agreed, I don't know, on meeting or something. Oops. Okay, now I can spell. And then, so each one of these gets converted into a word vector. Through
embeddings, right? Embeddings.
Right.
Yeah.
Right. And then, so if your convolution the first layer of the convolution will focus on maybe the first 3 words. The next layer will focus on the next 3 words. I'm sorry, the next neuron in this. So this is layer 1. And then in layer 2, so layer 1 neurons are here. This one sees that. Here's another layer 1 neuron, etc. And then layer 2 neurons would see 4 words. Right? Or does it 3 neuron? No, more than 4. This one goes. 5. It would see 5 words. So layer 2. So what we usually see in convolutions.
Even just drawing it like that, it starts to look more like the RNN picture.
Mm-hmm.
Well, RNN, it looks like the RNN because if you unroll the RNN in time, that's what it would look like. but this is not unrolled in time at all. So, so I think it's quite different. But you know, it's what we usually see for convolution networks for images. But so these are supposed to be one-dimensional convolutions. But what confused me is that, you know, the word embeddings here, this is another dimension here for the word embeddings. So what the reason they call it a one-dimensional embeddings is they take the embedding and they concatenate it. So that's the embedding for they, that's the embedding for agreed, that's the embedding for on, etc. So if you can concatenate this, then it becomes a one-dimensional convolution, one-dimensional kernel. So so for example, this kernel with this neuron here, its convolution is one dimension like that. So I put in the in the chat, I put in links to this paper, which is, I think, really in this paper they use convolution neurons. They have an attention model, and you know, they claim state-of-the-art stuff. But yeah, I think that's pretty much all I have to say there. That's all I understood.
So just to get this right, a 1D convolution over a vector means that your kernel are like, if you have a 3x1 kernel, then it's like a 3-number vector you pad over the embedding, right?
When you say 3x1, you mean 3 words?
No, 1 word. So when you do the convolution, you have to, so in the 2D space, it's like padding a rectangular filter over the 2D matrix, right?
Yes.
And in 1D, you have 1 vector and then a smaller vector that you pad over?
I'm not sure about padding. I mean, here, if you're looking at the middle of the sentence, there's no padding involved.
Yeah, I don't think padding is necessarily the right word, but kind of scanning over or sliding over.
Yes,
that's what I meant. Yeah.
You're right. You're sliding over. You're taking 3. The first one, you're taking 3 words, and then you take a 1-word step. I think they call it steps in convolution.
Yeah.
You step over 1 word, and you look at the next 3 words. You know.
Yeah. Wrong word. That's what I meant. Yeah.
Yeah.
What does that mean if you've got these 3-word vectors concatenated? Is your window the size of 1 word and you're scanning over, so your convolution is like part of 1-word vector and part of another word vector?
Well, your window size is 3 words. And so for example, let's say these embeddings are like 50 neurons or 50 feature embeddings, right? So so in this first neuron here, its field of vision is really 150 input lines.
Got it.
Okay.
So you're going a word at a time, basically.
Yeah, you're stepping the next neuron. Yeah, it's a one word step to the next neuron in the layer.
That seems very counterintuitive to me, because many languages put words at different parts of the sentence. So really, the key to this is the sequence of words, not the presence of words in the group.
You know, I would argue that sequence matters less. I mean, there's here, this is a little bit, this is not really.
I get it. No, I know what you're saying.
Okay. Yeah, sorry about this.
No, it makes perfect sense. Yeah.
Okay, yeah. But the reason why the reason why they do convolutions is the advantage is they can parallelize easier. If you're doing recursive neural networks, what you're doing is you're feeding it the whole input sentence at a time. They agreed on meeting. That's a serial step. Even and then you have to read the whole sentence before you can start processing the the target into the target language. Whereas in convolution, you're reading the whole thing at once. Timing matters less. Timing is taken into consideration with the receptive field of your neuron, somewhat, because each one looks at a small bit. They're basically looking at n-grams. So, yeah.
How did you get a sense of like how wide the typical early layers are for this kind of thing?
I think it's pretty small. I have 5 or 10 words. I'm sorry, maybe even 3 or 5 words. I think that might have been the case in.
Yeah, I was thinking with a sufficiently wide initial layer, you can capture all of the positional information. But if it's very short, then that would suggest that it's not all that important.
Yeah, well, even if I think even with a wide receptive field on the neuron.
Well, less a wide receptive field on the neuron and more neurons in that first layer.
Oh, more neurons. So yeah, the more neurons then will allow you to I think take smaller steps, but
Also,
I'm not sure.
This is a model on words, and Jeremy always did it on characters, right?
Yeah. Jeremy did a character model. But here we take the words and we do word embedding, and then we.
Yeah, you can get more when you have words than just letters or characters.
If the words have similar semantic meaning in both
You
languages.
have more meaning and stuff, I think.
What seems magical to me is that there is such a high correlation between languages that's surprising. I mean, I'm not doubting the research, but it's just surprising that these things work so well based on assumptions of proximity of words and the fact that words in one language match words in another.
I'm not so much into NLP, but what I really recognize is that the Google Translator, it's awesome. So it's in the last 2 or 3 years, it's so good in really getting all the little things you have in language. It's really awesome. So it's almost no post-processing when I translate German to English, for example. It's almost no post-processing I need. And that was really different a few years ago.
Yeah, it is really good, and it came out in basically 2017, late 2016, early 2017. But if you go and I guess, where is it, this timeline? And this is a Stanford lecture, and and he gave an example. The Chinese to English translation still needs a lot of work, even with Google. So he has this one sentence that he uses as a benchmark, and it's still it does it like a 70% good job. Not quite.
Yeah, that's probably more complicated, but I mean it's even getting idioms, for example, and that's something that's very it's very hard even for me, for example, as a native German speaker. It's very hard to know all these things. Just because that I can speak the language does not mean that I can know all the idioms, for example, and that's working so good now in the translator at Google. That's really awesome.
Yeah.
I don't remember if we talked about it in this forum or not, but in the interview I did with Jeff Dean, one of the things that just blew my mind was when he talked about how their original translator system was 500,000 lines of code. And after they went to neural machine translation, it went down to 500 lines of code.
Yeah, crazy.
That's like a few pages, right?
Yeah.
Yeah. I mean, I think the other thing I did not cover is the attention in the last couple of years, and that's been really helpful, I think. So yeah, there's an attention block with the colored stuff here that I haven't quite grasped yet. But it basically says when you're on a word, it looks at it tells you what words in the source text that you've seen that you should give more weighting to? You know, more weight means more attention. I think that's basically what it is. But I'm not sure.
Yeah, I can share a post that I was reading earlier that has a little bit on that. I thought they did a good job explaining it.
Oh yeah, I'd love to see it, please.
Let me. All right, so this was from, I started here this fall of RNN LSTM, and he linked to a previous post that he did on attention modules. And basically the idea is you've got an input vector, and as a way to try to model this idea of paying attention to certain things, maybe if you're focusing on a specific word when you're doing a translation, you know, you're focusing on that word or the words around it, you kind of multiply your input vector by a weight matrix that essentially determines how, what parts of that input vector you pass through. And there's this concept of soft attention and hard attention. Soft attention is you're essentially doing a linear combination of your inputs. At least that's it doesn't say that here. It says that the weights are real valued. It doesn't say that they add up to 1. And maybe that's not required, but in soft attention, you're passing in, you're essentially weighting your input values and passing those through. And hard attention, your weights are binary, so you're selectively passing some inputs through or not. And the interesting thing about this is that the reason why these attention mechanisms have developed the way they do is that in order to learn all this stuff, you need to keep it all differentiable. And in order to maintain that differentiability property, basically you there was another, was that here they were talking about that? There was another post I found on attention, and I'll share the links to all these. They're actually over here. But in order to maintain this differentiability, you basically, as opposed to building a network that looks at particular things and kind of shifts its focus in a hard way, the network looks at everything, but it applies this weight matrix, which is that's what we call these attention blocks. And the kind of reason why that's evolved is because of the differentiability. So this is another good article. Well, I actually haven't read this. This is another recommended article, I should say, on attention and neural networks. And this one's applied to visual examples. So I haven't read a ton of it, and I don't have a super strong understanding of how it all comes into play, but it is something that I read about and hear about fairly frequently, and I think it's an important concept.
Yeah, it's important enough that I've seen, videos and papers about that's titled "Attention is All You Need."
Mm-hmm. Yeah, I remember that one as well. The other thing I was thinking of when you were with the encoder decoder model was this slide that I use in a presentation. Like it's not just translating from one language to another, but this whole sequence to sequence or encoder to decoder model is used for a ton of different things. Here it's talking about image captioning and translation and transcription, but there are a whole bunch of other examples that use the same encoder decoder type of a model.
I could not read the post on that you should drop RNN and LSTMs. What do you think about this? Should you?
So I didn't get to the end of it. I got about to the attention part. I pulled it up this morning, but it's referring to, I think it came out around the time of this paper, which was, I think it was Mahesh that shared in Slack that Andre Karpathy was tweeting about this recently. So this is a paper that I want to take a look at. It basically is trying to evaluate using convolutions versus RNNs for different types of sequential tasks. One of the things that so they kind of talk about the different types of temporal convolution networks, causal, dilated, and other things. This image here, again, this is all kind of me scanning this. This looks a lot like what I've seen with Google's WaveNet, the way that that's represented. And then they talk about these different sequential modeling tasks that can be used to benchmark this. And then they are comparing performance, like for MNIST, these different types of MNIST for 3 different types of RSTMs, LSTMs, GRUs, and vanilla RNNs, and these temporal convolutional networks. And I am assuming that because these are all bold, it means that the convolutional nets are outperforming all the rest of these. But again, I haven't dug into this in any level of detail.
Yeah, I think the convolution networks are getting near state of the art, or but that's not necessarily why it's better. I think the reason why it's better is performance. I think in this paper you're showing it, they say their performance might be like 10 times, or maybe the other paper I showed is like 9 or 10 times, faster in the forward pass in translating a sentence. The other, also in training, supposedly the recurrent networks take a longer time to train, probably because of the serial nature of the task. Whereas in convolution, it's not serial anymore. It's parallelizable. You can take advantage of your GPUs better. So I think it's in training, it's also faster. So the advantage is I think in terms of performance.
When you say the advantages in terms of performance, you mean computational efficiency as opposed to task performance or accuracy?
Yes.
Got it.
Well, if it's task performance, I would call accuracy. But so performance means faster.
Yeah, so this, the generic TCN architecture outperforms canonical recurrent networks across a comprehensive suite of tasks and data sets. Of course, they could mean, and when they say outperforms, they could mean time here, but I think they're talking about accuracy loss and things like that. So it's not just computational.
Right.
They seem to be implying here that there's a performance benefit as well.
Yes.
Cool. I suspect that a future version of the Fast.ai course will be talking about this stuff as well. Attention and CNNs for this kind of stuff. It'll be interesting to see how they incorporate this stuff into the class. I'll put these links in the chat as well. Let's see, where are we? Okay, so any thoughts on the lesson? How did everyone do in terms of getting through this lesson, the first half of this lesson at least?
I fell asleep.
Is this the one that started off with the image stuff and then switched to RNNs? I'm trying to remember.
Other way around. Started off with RNNs and switched to the image stuff.
Okay. A while ago, I'm sorry.
Well, I just tried to get the concepts. I did not code anything for RNNs.
Likewise.
To me, RNNs are a world unto themselves because of the loopback aspect of them. I know Jeremy tries to unwind it and demystify it, which is a very bold move on his part, but intuitively, I struggle with the idea of LSTMs because I don't know how long the memory is. So like there's this idea of this loop, but there are many loops, right? There are loops that go for weeks, there are loops that go for seconds, there's loops that go at all these different lengths, and I don't really understand how they can codify all these different time lengths in one fixed loop. So it's kind of counterintuitive to me.
Is Andrew on? I saw Andrew in the participant list earlier. He shared a bunch of presentations from some Fast.ai study group that he was doing in London.
Yeah.
Has anyone taken a look at these?
Yeah, I went through them all. They're very good, actually.
Yeah.
Yes, they're really good.
So, David, going back to your point about LSTMs and how it can go back through all this time, I think the attention model, the attention's way of doing it is an alternative approach, and supposedly a better approach in terms of accuracy for this sort of long-term memory, remembering, you know, how 100 words ago might affect the current word.
Has there been any, did you come across any work where they try and maintain context across sentences and across long periods of time so that you could actually get into a conversational style of NLP? I mean,
I didn't see that, but you know, I would imagine, I think so.
yeah, but it wasn't explicitly mentioned. I'm just curious.
No, I haven't seen it. I haven't looked at it.
Thank you.
And specifically for conversation, you're asking about the
biggest problem, the biggest stated problem with NLP in terms of user experience right now is that the agent that you're interacting with keeps forgetting the context. So you say, my son needs to go and buy a shop of, go to the shop and buy some milk. Oh, could you let my son know he also needs to buy some?
Did you see the Google Duplex thing on their conference? That was pretty awesome in terms of understanding context.
I missed that one. Very curious.
It's this system where you can tell the Google Assistant that, for example, it should make an appointment for you with for a haircut or something. And
yes,
then,
that one. Yes.
And that's pretty impressive.
Very impressive. And I'm guessing my assumption was that was based around keeping attention going. So you might have specific neurons that refer to specific concepts, and you essentially just keep them primed or keep them going to try and maintain the context over longer periods of time. That's my intuitive guess. I'm curious.
I mean, it's certainly geared towards having this conversation about making an appointment, for example. You will not talk with this system about Nietzsche or anything, but when I saw this, I was really stunned. That's really, really impressive.
Yeah, it was definitely impressive. They send into the model a ton of contextual information about the nature of the request and the details of the request as they know it, in addition to kind of the pure language type of information. And they use all of that to determine what the response is.
So the phone number that you dial is in their database, and they know that that's actually a pizza restaurant and that these things are on the menu, that kind of thing. So they've essentially pre-baked the this is very good. I'm not saying it's a bad idea, but they're essentially...
Yeah, but I mean, they had this one conversation with this not very good English-speaking woman, and they really had this funny conversation, and it was really like a real person was speaking to the woman on the other side of the phone.
Yeah,
if you did not see that, you have to look at it.
This is the PDF. It's they're calling to make a reservation in a Chinese restaurant, and there's a ton of background noise. The speech is very heavily accented. It is incredible that, and basically the duplex system is asking to make a reservation, and the woman is basically saying you don't need to make a reservation, and it eventually figures it out. It is very impressive. So let's see. So we know any particular roadblocks or any other thoughts on the on this lesson? It sounds like we're all sounds like we're all kind of running out of juice on this class, to be honest. I'm not going to lie. I was there several weeks ago because just things are super, super crazy for me right about now. But I think the material is interesting, but I haven't had as much time outside of kind of in the mornings prepping for the call, like doing a lot of background research and, coding up a lot of variants of the lesson and things like that. Sounds like I'm not alone in that.
No. I was wondering what you guys will do after this course, or how you wanna go on with digging into this topic.
No, I think first of all, this course has got too many difficult concepts. If once you really start digging into it, so you could spend the rest of the year just trying to figure out all the concepts that have been taught once you really go into the detail. I had a question on this course, if anybody can help me. We had briefly discussed this last time on the standardization of the terminology. Now Jeremy has used these ovals and these rectangles and these triangles, to denote the activations and to denote the inputs. Does anyone have any suggested alternative terminology which can be used to visually depict a neural network?
I think that's one of the big outcomes for me from this course. I will try to go to the mathematical notation and not this kind of graphical notation that most people have for this classic NLP neural networks. I had several moments where in this course where I then saw an equation, or not directly an equation, but in the code. And then I thought, okay, that's just really a matrix that is multiplied with this matrix, for example. And I think I would try to transition to this notation.
Well, I would fight you tooth and nail on that, guy, because the picture is worth 1,000 words to me. Except for when they do the unrolling neuron stuff, that really confuses me.
So
I thought this article was pretty good in kind of walking through some of these standard building blocks and providing links to other resources. I don't know if this is the kind of thing that you're asking about.
Yeah, if you see the video of the course also, he's using essentially three shapes. He's using rectangles, he's using ovals, and he's using triangles. Now, what I typically do is, to make things very, very simple. Wherever I have a noun, I use a square block or a rectangular block. And wherever I have a verb means, if there is a program, or if there is a process, I use a circle. So I'm just trying to figure out whether this is the standard terminology. I'll just give you a very simple example. For instance, while I was doing the preparation for this, for the Resnet thing, which I was talking about, even the depiction of the weights from one neuron to another, Andrew Ng uses a different terminology, and Michael Nielsen, whose book is very popular, on the net, he uses a different terminology. So it's very confusing, when you're trying to learn from scratch. So
Well, I think there is no standard, and I don't think that there will ever be a standard for that. So everyone is kind of having a different picture in his mind, and I think Jeremy's is pretty good. You can read that pretty good, yeah. Especially the unrolled one, but there are so many different kinds of showing this.
Yeah, and I thought this one, Jeremy's. I thought Jeremy's was just kind of a reinterpretation of Karpathy's. I think it was Karpathy's that had a very similar set of pictures in it. Maybe I'm thinking of a different one, but I saw a paper or a blog post or something that had a similar set of pictures to Jeremy's, and he just kind of color coded things in a nice way.
Yeah, Kai, hey, going back to what you said about what's happening next, I think I'm just gonna maybe dig into course, the second course, or I may go back and redo this one.
I think I will try to go through the deep learning book.
Yep.
The book? Okay. So what's happened for me is I'm trying to blend machine learning with computer vision. And computer vision is as big as neural networks and moving just as fast. I mean, its heyday was a few years ago now, but thankfully it's not changing at quite the speed of the machine learning side. But there's so much material to cover in computer vision. I mean, if you can find a pure application for machine learning, I think that it's great to just focus on machine learning alone. But if you're trying to apply it to a problem, there's usually, most problems anyway, a ton of literature in that domain already. And really, like if you look at SIGGRAPH this year, the Computer Graphics Conference, the biggest papers are the discussion of machine learning with computer graphics and also in computer vision. So we're into the era of synthesis where we can take these amazing technologies and then apply them to fields which already have a history, and that's where the real breakthroughs are being made in terms of applications. So I've had to divert quite far away from this course and study machine vision, which is really, really amazing stuff. So yeah, is anyone actually applying this in the workplace, or is this mostly just in skill improvement and career development?
Oh, I did use neural networks for approximating stuff in for the calculating the power output of a motor, of a hydraulic motor. But that was I mean, this classic neural networks that you used even before the time of deep learning. And a few years ago, I coded a neural network in C#, but no deep learning. No deep.
I actually found the transition to Python quite pleasant. I actually quite like Python. I've never used it before until I started this course, pretty much. I'm
mostly using R, but Python is but Python is really good. This whole concept of PyTorch is really good. I've never seen anything object-oriented in the world of, let's say, data science that work that goes, because it's, I mean, data science, it's more a functional way you do things. But for this neural network things, and PyTorch is really great for that.
Yeah, I just got Docker working myself. I've taken the plunge in actually learning Docker, and I now have a system where I can run different machine learning stacks side by side, which is quite remarkable.
Yeah.
Yeah, so for those of you who are struggling with pip and Condor and Anaconda and all the others, they're well worth understanding what they are, but the real elephant in the room that I found at least is Docker. Docker is
I'm doing that all the time, and it's great. It's taking so much of this installing stuff from you away. That's really awesome.
But are you using it on your local machines just for playing around? Because I find that a bit like overkill. I'm just using virtual environments on Python and to kind of keep everything tidy and clean.
Yeah, I have 4 machines in my local cluster. They're all GPU based. Okay. I got a long way with Anaconda, with the idea of Condor having separate environments where you could essentially have some separation. And I also use separate machines to have separate stacks. But now what I'm doing is I'm actually unifying all the machines on Docker, because you can actually run seemingly incompatible.
Yeah.
Yeah, but for laptops, I mean, for me, that's always overkill. I mean, if you have a decent workhorse, like small cluster, then the power is there anyway. But just for a dev laptop, I find that like RAM consumption and everything is pretty heavy.
No, but it's when you use Windows or Mac, then that's true. But when you use Linux,
yeah, for Linux, it's probably different.
Yeah. It's no overhead at all. It's just
right.
just a new file system you mount, right?
Right.
Yeah.
It is. I'm not saying it's easy.
I was playing with it too.
But
yeah.
It's worth it. It's worth
yeah.
it.
It's an expensive buy, but it's well worth the investment. So,
meaning the small GPU cluster.
For the beauty of what I'm doing in Docker is that there is literally nothing to do to take it to the cloud.
Yeah, and if you have so let's say you buy a GPU cluster for yourself, then you can just download the NVIDIA PyTorch image, and you are completely ready to go. No installation, nothing at all. That's
yeah.
really
awesome.
I
see the point for the deployment. That should be really cool. I was thinking about that as well. But I want to have an environment which is kind of seamless. If I want to push it to AWS or to our HPC at work or something like that. For this kind of stuff, I see myself learning a lot more and make it happen.
Yeah. The Docker tutorials on the Docker side, I think they call it Docker Classroom. Very good. Very, very good. So.
I've definitely spent too much time in my life on installing things, and now I do it once, and then I can just port it to any machine I want to.
Hey, David, what Docker tutorials are you talking about?
So if you go to docker.io, I think it is, there is what they call the Docker Classroom.
Okay.
I'll post the link. Let me post the link. I'll post it in Slack after the call.
Okay.
No, it's really good. Yeah, no, I spent a lot of time looking into Condor and to all the different ones, yeah, Docker definitely is the way to go.
Just for the Python guys, I mean, I would say I'm really getting into PyEnv and pipenv, the new kind of kids on the block, and that's actually pretty decent. I mean, there's so much stuff out there, it's a bit confusing, but if you focus on these recent developments, that's really cool as well.
My Python environment has gotten so dorked up with all these different environmental.
Yeah, that's what I mean. I mean, I was
PyEnv, and there's also PyEnv virtualenv that will manage a virtualenv from PyEnv, and it's just I don't do it enough to kind of learn it for good. And
yeah, it's a bit funky, but once you get in there, it helps.
Just wanted to share a viewpoint since people have been talking of Docker. You know, Ria had asked a query on ONNX on the Slack group. So I believe ONNX is a very powerful, abstraction in which your machine learning models can be, transported across environments from training to inference. So this is something that I will definitely, look into it in the near future.
Yeah. By the way, is that this Ria Cherubo, this prodigy child? I saw a video on her, and I think
I don't know.
Kind.
Yeah. Even I felt, because she's, she's the only one whose name came up in the. So I mean,
Yeah.
she's 14 years old and she's gone into Harvard. So she's brilliant.
I remembered her name and I googled her, and then I saw the documentation on her.
Yeah. No, which I feel personally very happy, because if you have young, there was another young kid who was earlier asking a lot of questions. He's no longer there, I think, now on the Slack, or he's not very active, because really at our age we find it difficult to learn, but these kids can really learn much faster. Yeah.
I wanted to ask, has anyone looked into the second part, like how that's gonna go down? Like is that in a different style, or does it divert from the current one? Did anyone peek into the second one?
No, in this lecture 7, Jeremy mentions that you need to master part 1 thoroughly well before you get into part 2. So
did anyone actually do 1 or 2 sessions there?
No, I have not done it.
Yeah, my impression from part 2 is that it starts switching gears to looking at research papers and implementing them. But I haven't looked at it personally myself either. David, did you look at the?
I did look at a couple. Yeah, no, I did. It's very good. I don't know where my Zoom window has vanished to. Let me see if I can find it. No, I didn't see it here. No, the Zoom window has. No, I can't see you anymore, sadly. Anyway, no, I did look at them. Once again, the ones that I was most interested in are in the computer vision space, and in order to really grasp that stuff, you need to do a lot of work on computer vision to bring your knowledge up to speed, so that you understand which bits are being done by neural networks and which bits are being done by very clever algorithms that identify things in videos and in images.
So I was wondering, because for me, I mean, Sam, you mentioned that basically the motivation kind of went down a little bit in the last month, but it might have been the crazy summer here as well, temperatures and just busy month. But I was wondering if the other one is I don't know, more motivational.
Yeah, and I think my kind of net takeaway with this course style is that it's got the pros are that it is kind of very contemporary, very cutting edge. It is incorporating in, these little tips and tweaks that he's pulling from, research papers that maybe just were published a few months ago or something like that, or maybe older, but no one, really knows them. And it is kind of focused on, very practical implementation ideas. The con, I think, is that in order to really, you just have to have a very, very high level of self-motivation in order to, I think, get as much as you can out of the course. And you have to, I think, have the time to support that self-motivation. Whereas, something more like what we've all seen with the Andrew Ng courses, it's there's a track. You go through, the lessons in the track, you learn a fixed set of things to a fairly reasonable depth. And you don't have to, I think where the self-motivation and the time come in is you have to invest a lot of time with the Fast.ai course, just deciding what it is that you want to learn more about and studying that independently.
I wasn't really sure for myself, to be honest. I mean, I like the videos very much.
Mm-hmm.
Really cool style of teaching and really engaging, and the size was fine as well. Maybe it was the mixture of all these topics, like going so fast from NLP to vision to categorical stuff, which was interesting, and then this kind of bitwise hopping around, which is kind of a cool overview, but also, yeah, as you say, demands quite a lot of actual work.
Yeah. I mean, I'm very happy that I went through the course. I don't think I'm going to jump right into the second one before coming back to this one in some period of time. But for me personally, I want to kind of go back through some of the more fundamentals and, make sure I have a really much stronger understanding of backprop and, the way matrices flow through some of these networks. So I think the book is probably the next step for me as well. But I think the course, is a great course. It's interesting that across these bunch of weeks, we spend actually a lot of time talking about the course itself and the structure of the course, which says something. I'm not sure what exactly, but it definitely says something. Cool. So I think we're at the top of the hour. Next week, we will finish strong with the second part of lesson 7. We go back to the image processing topic and the CFAR data sets and get to kind of refine the understanding that we developed in the first 3 lessons. So that should be fun. And we can talk some more about what we're all planning to do after the course.
And last time to have a little presentation. Last chance.
Yeah. There was some study group kind of discussing. Yeah. We'll discuss more next week, what folks want to do to continue, and if there's, if we want to have some kind of study group or kind of merge these into the other meetups or what.
Yeah, Kai, I had I had posted on the Slack group regarding that. So essentially the ResNet block, which is the figure 2, which is there in the paper, I went deep into it. I couldn't find any resource on the net. So I have tried to explain that. Now, is that something that we would want to do next week? My presentation is ready, but it's about 50 slides. So, it'll take about 20-25 minutes.
50,
so I don't know.
0?
Yeah, but I will go through it pretty fast. So
maybe a little shrink it a little bit down, but
no,
I mean it's interesting, definitely. But
no, I think it's basically very simple stuff because my problem with this course really has been he's really moved very fast. So we need to certainly, because once you start digging into the details, you realize your lack of understanding of the details. So
yes.
So
I totally understand what you mean, but I mean we have 1 hour next time when we talk about the course, and maybe someone else wants to show something. So
sure, no problem.
Just time-wise, it would be better to have a little bit less.
Fine, no issues,
okay.
No problem. Yeah, okay.
All right.
I think as long as you can kind of scale it back to something manageable, 10 minutes or something, that sounds good.
Yeah.
Okay.
All righty. Have a great weekend, everyone.
Okay, thanks.
Bye.
Hey, everyone.
You too, guys.
Thanks, guys. Take care.
Thanks, everyone. See ya.